In this video, we'll be talking about the idea of a composite function. It's possible to combine functions to make new functions. Well, why might we do that? The reason why we might try to combine functions is because functions bring along with them some very useful mathematical rules. But at the moment, we only know those kinds of rules for the concept of a function or simple functions. If we can figure out how to combine functions in different ways, we can extend the rules that we have to apply to these new functions. We can use a basic function to represent a less basic situation. But we need to be able to do this in a proper and appropriate mathematical way. The idea that we're going to use is what's called a composite function, and that's just a function of another function. So the little box we've got here gives us a pretty good idea of how that works. Basically, we've already seen this half of the picture. We have an input value x going into some function f, which pops out at the other end another value, f of x. In other words, f changed x into another number, f of x. We're going to think about this in an extended way. We're going to take that value, f of x, and plug that into another function, g. And that will give us out a new output value, g of f of x. And that's the idea of a composed or composite function, the function g of f of x. Essentially, what we're doing is using one function as the input to another second function. Now, something important to note in general is that f of g of x is not the same as, that's what this symbol here means, not equal to, g of f of x. So the order in which you compose the two functions, or which function you put as the input to the other function, it actually matters. So we can't just switch them around willy-nilly. So let's have a look at an example. Suppose someone says to you that it doesn't matter what order you compose two functions, that you always get the same final output. We need to use these two example functions to prove that that person is wrong. So maybe have a go at that now. Try pausing the video and see for yourself the difference between f of g of x and g of f of x. Okay, so what does this mean, f of g of x? Well, basically it means take the f of x function and everywhere you see an x, replace it with what g of x is. So we're going to have f, instead of just x, we want to replace that with 1 minus x all squared as the input to the function. So here, where we have an x in f of x, we want to replace that with 1 minus x all squared. So we have 3 times 1 minus x all squared, and that x itself is squared, so we need another squared out there. Plus 2 at the end from here. And then all we need to do is bust that open. And really the only reason we're busting it open is because it'll be easier to compare with g of x in a moment. So let's just quickly do that off screen. Okay, so we expand out the brackets and we've got 3 times 1 minus 2x plus x squared, all squared again, and plus 2, remember that at the end. Now expanding this squared bracket out, we get this long ugly thing here, which of course we can simplify just by combining the like terms, put all the constants together, x's together, the x squareds and x cubes, and that final little x to the 4, multiply by the 3 out the front, and finally add 2 as well. So we get this nice little polynomial here. So that's f of g of x. Now let's have a look at it the other way, g of f of x, and we're hoping to show that these two things are different. Again, we're going to be taking g of f of x, so that means we want g of whatever f of x is. So our input is going to be 3x squared plus 2, taken directly from up here. Now g is the function 1 minus x all squared, so we're going to be replacing that x with 3x squared plus 2. So we have 1 minus 3x squared plus 2, and that whole thing is going to be squared. So we can simplify that. We're going to have 1 minus 3x squared and minus 2, so we're left with minus 1 and minus 3x squared, and the square remains out the front, and we just want to bust that open now. So we can write it out in full, and then just do the multiplication out, the distribution. So let's just quickly do that one off screen. Okay, there we are, 1 plus 3x squared plus 3x squared again, plus 9x to the 4. And we can just simply clean that up, bringing those two middle terms together. Which of course will be 6x 4x squared plus 9x to the 4. Now clearly that is not the same thing as what we have right there for f of g of x. So we can say that's not equal to f of g of x. And so we can say in general, g of f of x and f of g of x will not be equal to each other, because we can see that it's not true in this one case. So it can't be true generally. Okay, so that was a little bit general, but what are some other things we can do with composite functions? Here are some handy examples of ways we can combine functions. We can multiply functions by scalars. We can add and subtract functions from each other. We can multiply functions. These are some ways we can combine them. And these bring up some handy properties. We have a distributive property. K times a sum or a difference of functions is k times the first function plus or minus k times the second, and so on. We can change the order of multiplication, and we can also bring an index law in like this one here. Now note that this notation might be a little bit weird or a little bit different. If you haven't seen that before, it just means the nth power of f of x. So it's almost like we're doing something like this. Okay. Alright, so some more examples. We've got two functions here, f and g, and let's look at writing the following function compositions in an expanded sum or difference form. So again, why don't you pause the video, have a go at this one yourself, and then come back to see what we've got. Okay, so first up, m of x is 4 times f of x. So we're just going to go 4 multiplied by the function f of x there, and we just expand that one out to get 4x squared plus 8x minus 4. Okay, in b we have m of x is f plus 2g. So we've got our f there, x squared plus 2x minus 1. G, we want to multiply by 2, so we have 2 by x plus 3, which we can replace with 2x plus 6. And then adding the like terms, like powers of x, we get x squared plus 4x plus 5. And in C we have m of x is g cubed of x, or the cube of g of x, so that's x plus 3 all cubed. And if we want to run over to the side here, we can bust that open as x plus 3, and x plus 3. Simply expand those ones out. We're going to get x squared plus 6x plus 9 multiplied by the x plus 3 at the end. We'll get x squared plus, x cubed plus 6x squared plus 9x and plus 3x squared plus 18x plus 27. And we can just simplify that, bringing the like terms together. So we have x cubed plus 9x squared plus 27x and plus 27 finally. For our last question, m of x is just the product of f and g. So we can just put those in, x squared plus 2x minus 1 and x plus 3. We just expand those brackets out. We get x cubed plus 2x squared minus x, moving across these ones, and then plus 3x squared plus 6x minus 3. And finish that one off, just bring together the like terms. We've got x cubed, there's some 5x squareds, minus x plus 6x is plus 5x, and finally minus 3. So that's our composed function there. So that's a few examples that we've got. Let's have a look at one final thing before we finish this video off. It's the idea of shifting functions. Now, these ones are really quite useful. Shifting a simpler function is a useful composition that allows us to look at moving graphs up or down, like we see in these two graphs here, or from left to right, as you see in these ones. And it's actually quite a simple thing to do to change those functions. Now in all of these pictures, the dotted line function that you can see is the function x squared. Now what we've done in the first picture is moved it down by 0.5 units. So you can see it's crossing the axis there at 0.5. To do that, it's as simple as just taking minus 0.5, tacking that onto the end of the function. And in a similar way, on the right here, if we want to move up by 1 unit every single point on the graph, we just add 1 to it. So we get x squared plus 1. So moving up and down is as simple as adding that value onto the end. Moving left or right is slightly harder, but not really much. So you can move here. See here in the bottom left figure, we've moved from the dotted line across to the right by 1 unit, and all we do is change all of our x's to x minus 1s. So x minus however many you're moving to the right. So instead of x squared, it's x minus 1 squared. And of course, if you're moving back to the left, in this case by 1 unit, it's going to be adding 1, so x plus 1 all squared. So if we were moving back to the left 7 units, it'd be x plus 7 all squared. And that's basically how we can compose or shift functions left, right, and up and down. So let's check out this example. Take a moment to read through this one for yourself, and we'll come back in a moment. Okay, so I hope you've had a read. Basically, we've got the trajectory of a small rocket fired from a testing facility located at this point right here, minus 1, 0. It's known to be well approximated, the trajectory that is, by the parabolic graph of the function. So you can see there is the graph, f of x equal to minus x squared plus x plus 2. So that there is the graph of that function. So we're told that the facility needs to be moved 2 kilometers to the right. So you can see we're starting to talk about a shift here, 2 kilometers to the right. And it needs to be done for geological reasons. That's really irrelevant here in our question. But the point is it needs to be moved to the right. We want to know what will be the new function that describes the path of that rocket. So let's think about that for a moment. Essentially, we want to move 2 units, or kilometers in this case, to the right. Looking back, we saw that if we wanted to move to the right, that was this kind of situation, we need to subtract the amount that we're moving from x everywhere that x occurs. So in this case, we want to have our new function, let's call it n of x, will be f, not of x, but of x minus 2, because we're moving 2 kilometers. So that's just a matter of changing all of these x's into x minus 2's. So we'll have minus x minus 2 all squared plus x minus 2 plus 2 on the end. If you like, you can expand that one out, and you'll find that it's just minus x squared plus 5x minus 4. And that'll be the new function, which essentially looks something like this. Okay, so that's our trajectory of our rocket once it moves. So where to now? As usual, try the worksheet problems. Write down in your notebook any questions you might have, or things that you need to figure out. And a new one, start up a cheat sheet for yourself, perhaps in the back of your notepad or workbook, and write down any rules or important formulae that you've seen so far, not just in this video, but in others. As we move through the semester or through the course, just add to that cheat sheet every time you see something that you think you might want to remember. Anyway, that's it for now for our composite functions video. Move on to the next video once you've finished with